Go ahead. Take the derivative. That's what I want to see. Because the point I want to make here is exactly what happens with the notation for these types of derivatives. If you were to derive this, hopefully you would say that is 12x squared, because that exponent is 3. This exponent is -1. So when I multiply by -1 and then decrease the power, now it's -2. But what do I write here on this side? What is it for y? We're just looking at this with the chain rule. Here's y's, here's x's. I want to find the slope. How is the y value changing in terms of the x? Easy enough. Now for the next one over here, it's kind of the same thing, but with different variables. So with different variables, what should I put on the left side now? dy over dx? It makes no sense with the function that we have. We're looking at how v is changing with respect to t. And even for this last example here, if I were to say, wow, you need to take the derivative, you're going to use a whole lot of chain rule. I mean a whole lot of chain rule, like 4 of them. That's what I call the quad 4-part chain rule, and you'll notice not one single step of that is difficult. You just have to learn how to separate it correctly. This is the innermost, and then next, and then next, and next. Or outermost, and next, and next. Some people are better at starting with the inner function. Some people are better at starting with the outer. Figure out how you learn and do it your way, okay? So I'm not concerned which method you use, but you will need to take the derivatives. And oh my God, there's so many derivatives. But I want to look at, hey, I have a w and an x here. What happens with that derivative there? What variables do I use? It's the same thing you've been doing for chain rule, which brings us to our next topic. It's called implicit differentiation, and it's how you take derivatives when something might not be written as a function. It's not written explicitly. Explicitly written functions, explicitly written functions, or explicit functions are written as y equals. When you put something into your calculator to graph it, you have to write it explicitly. The dependent variable, the y value, is all off by itself and everything else is on the other side, which is lovely, but things aren't always set up that way. These babies, implicitly written functions, have x's and y's scattered higgledy-piggledy all over the place. You'll notice these first two are exactly the same. They're actually just written in 2 different ways. One's written explicitly, I'm defining y equals something. The other one, the y's and x's are scattered. This one, same thing. Same function. This one I did have to change a little bit. But there's lots of equations out there. They might not be a function, but they're equations where the x's and the y's are scattered everywhere. So to learn how to derive things implicitly, you've already got all the basics. You just have to adjust your derivatives for any variable other than x. Here's how. Let's say I want you to take the derivative of these nice little values here, and the derivative of 5 is 0, 5x, 10x, and 20x cubed. Let me introduce you to the power rule. Oh boy, great. But this is more interesting. What's the derivative of 5y? Well, no, this is still 5y to first and multiplied by 1. Y to 0. Oh, but this variable doesn't match up with that one. If the variables are different, this answer is going to be a little different. You get 5 dy dx. Why have we never done that before? Oh wait, maybe we have. Were we really paying attention? When we did equations like this, it was real easy. We concentrated on how to find the derivative of 5x squared. But did we pay much attention to this? Y to the first power, which would normally just be 1, happens to be dy over dx. Every time we write out the derivative for y on one side, because it was explicitly written, we just threw down a dy dx and figured that was the end of it. There's more to it, you know. Follow next video.